Hello everyone, I'm your host Adi and you are watching ABCTechLab, your coding buddy. In this session, we will discuss the process of constructing an e-commerce application architecture using AWS, that is Amazon Web Services. I have specifically designed this content for AWS architecture interviews as this e-commerce scenario is very frequent topic in professional evaluations. We are going to analyze it thoroughly and observe how to build this system on AWS. While the completed architecture might look intimidating right now, we will reach that final state by talking small, manageable steps, right? Here are the specific details for the e-commerce architecture. I deliberately kept it short and brief. For the functional requirements, I will say like this defines the specific feature and behavior the system must support. For example, the product discovery, users must be able to browse product and use a search service to find specific items. And for cart management, we will say like a cart service is required to manage items a user intend to purchase that. And for order processing, an order service must handle the end-to-end life cycle of a purchase, including complex background activities like inventory update and shipping coordination. For payment handling, I will say like the system must process transaction securely through a dedicated payment services. Now for user management, the system must support user sign up and sign in and authentication via an identity provider. For recommendation service, we will say an AI driven recommendation engine which suggests product based on user click stream data and purchase those history. For notification, the customer must receive update via email or SMS or mobile push notifications regarding their orders. Then the last one I will say like the business intelligence. Business user require a data warehouse and visualization dashboard to analyze top selling products and market trends. See, if you going to gather a lot of them, it will become so many. I'm just going through the minimum one. Now we will quickly go through non-functional requirements. This defines the quality attributes and constraint of the system. Like for example, first we will take scalability. The architecture must handle millions of users by allowing components like microservices and databases to scale independently based on the load. High availability, the application must remain accessible even if individual components fail, achieving by hosting web servers across multiple instances and using managed services. When it comes to low latency performance, we would like to say like to improve end user experience, the system must use a content delivery network, that is CDN, to catch static content near the user and in-memory databases for fast session retrieval. Data integration, for financial transaction, the system requires a database that supports strict schema and asset properties to ensure data accuracy. For flexibility, we will go through the product catalog must be able to store thousands of items with different attributes like laptops versus pens, just a cert, just different kind of items with different kind of activities. So we will try to incorporate MongoDB and all any NoSQL database. Later on, maybe I will introduce Amazon DynamoDB for AWS. So we don't want that rigid schema. And for cost efficiency, we'll say the design must consider cost, such as using Amazon Athena for cheaper ad hoc queries compared to the maintaining a full data warehouse for every small request. So yeah, like this we can briefly mention those functional and non-functional requirements. Let's dive in now. Our system will serve two type of clients, those on web browsers and those on mobile services. We will assume our platform name is ABCTechCom application and will have domain name www.abctechcom.in. Fine. To build this, you generally need several fundamental parts. First, this is the front end, which provides the user interface for our customers, right? Next is the back end, which houses the services responsible for business logic. Now this is the final. The backend must be supported by database. These three elements are the absolute minimum requirement for any application. To host the front end, we utilize web servers. These are usually hosted on virtual machines and we deploy several of them to ensure the site remains highly available and scalable. For the backend services, modern design favor a microservices approach. This means splitting the application's features into smaller, focused services. For instance, a product service handles the items shown on the landing page. A cart service manages user selections, and additional services handle payment and orders and all this stuff. By separating them, you can manage and scale each component independently, right? Modern applications also utilize different databases tailored for a specific task. For example, for a product and for cart, a NoSQL database is ideal. This is because an e-commerce application sells a very fast variety of items, right? So like laptops and pens and tools and some shirts and some shoes. So all they have different properties. If you check as the properties of this, because a laptop must have RAM, how much RAM it has, or the color of the laptop, or the CPU and all those things. But if you purchase any e-commerce platform from a shirt or book, so it will have different properties like ISBN number, or shirt will have the sizes. So this is why we prefer their NoSQL, because there is no fixed schema. Every entry in a NoSQL database can have unique attributes, making it perfect for diverse product catalogs. However, for payment and for ordering system, you need a SQL relation based database, right? Because it has transactional, it has atomic. So this requires a strict schema to handle transitions and ensure ACID properties for data integrity. You may allow users to reach both your front-end and back-end services, right? For the front-end, a load balancer is used to spread incoming traffics across your various web servers. Backend services are typically accessed as REST services, requiring an API gateway to route requests to the appropriate service based on the specific API calls. When a user first connects, the very first service they encounter is the DNS service. That is domain name service, right? This request for ABCTechCom.in goes to the DNS server, which provides the IP addresses for your load balancer or API gateway. Now the client has the IP. Their web or API request hit the appropriate gateway. To make this application production ready, we must add user authentication and management. You can use an identity provider IDP to verify users and issue tokens, allowing them to log in and make secure API calls. If the application experiences high traffic with millions of users browsing products, you need to optimize performance. Since these product details and images don't change constantly, it's efficient to change them in a content delivery network CDNs. Much like how Netflix catches movies at edge locations, right? Because near you, to avoid downloading every time, because so many people are watching the same movie on the same week or something, same time around in the same places. Like in India, some movie get launched, so many people will watch the same movie on the time, right? So every time it will go to database and hit the database and bring that, so it will become very costly. So what we do is we used to put the CDN, so content delivery network. So what it will do, it will put that in some cache memory for a static purpose, like static assets. So this includes, like for our e-commerce platform, so what we will do, this product like photos or videos or static HTML will put there in CDN. By storing this static data in external storages accessed directly by the CDN, what will happen? You significantly reducing the load on your web servers. Additionally, using an in-memory database to cache user sessions ensures they still logged in. So even if they return later, improving the overall experience. So whatever you saved or whatever in your cart or something like that, it won't go missing because of the cache memory, right? In phase 2, we now add more features, like starting with the search services. This is the critical for any e-commerce site, right? The search engine needs to know about every product on the platform, which means it must stay synced with the NoSQL database. If an administrator or vendor adds a new product through the API, the product service updates the NoSQL database, right? Because it is directly connected to product service. We want this update to automatically trigger this search engine to index new items, because we are searching through Elasticsearch database right now. We achieve this through event-driven execution, which monitors database changes and updates the search index instantly. When a customer places an order, it triggers a series of background tasks. You must update inventory and arrange their shipping and alert the customer. The order service coordinates these internal services and often interacts with third-party partners such as external shipping vendors like delivery or some other third-party vendor. So they will do those shipping and all. So what we'll do, we try to attach our API services to there to keep the customer informed, or a notification service. So this kind of sends updates like email or SMS or mobile push notifications. So generally we used to do through this. To suggest products, you need a recommendation engine powered by artificial intelligence, right? Because nowadays anything which has no AI, so it has no value. Building this requires access to all your data, like product information or like your purchase history and your reviews. So you use this to train a machine learning model to get real-time data on what users are currently viewing, or you can collect also click streams data, like how many who user is clicked it so many times, so maybe he is liking that like that. So it will be stored on your web servers. So this is continuous streaming data, and you also gather user and other data from your SQL and NoSQL databases using ETL, that is extract, transformation and load process. So this data is stored and used to train the model later on, and then it provides recommendation based on the service, like how many, just I said how many clicks someone has done, or like which is in trending right now. So based on this we can always give recommendation over there. For long term business strategy, you need advanced analytics on all those data produced by millions of users. This requires a data warehouse. Like first you gather all the dispersed data into a single data lake. From there the data warehouse enables heavy analysis, while business intelligence, that BI tools like Power BI and all those things tools creates your charts and graphs for stakeholders, because they don't understand the underpinning technical things. They will look at the graph and all those things and decide those business decisions. So for specific questions not in warehouse and all those things, you also need the ability to run ad hoc queries directly on your stored data, because suppose you had not queried something and some question arises all of a sudden and you want the answer. So what you will do, so you on that time you have to run some ad hoc queries to get the answer out of it. For that purpose you need some query mechanism so that you can do that. We can organize the architecture into distinct layers like DNS or authentication or content delivery or front-end, back-end, database, data lake, so many things like AI analytics. So it will segregate all those things and it will very easy for understanding and to lay out things in our mind map. Now let's map this to specific AWS tools, just what I was saying, because earlier it was very plain, right? So this is the front end. Hosted on Amazon EC2 instances right now, because within an auto scaling group managed by an application load balancers. So backend, see this is the backend. So backend will be generally use microservices and are hosted on containers like Amazon Elastic Container Services, ECS and all those things. So I'm putting it here. And for workflows, the complex logic of the order service is managed by the AWS step functions. And access and security, if you see there, so Amazon API gateway hosts the REST APIs, and Amazon CloudFront act as the CDN for us, and Amazon Cognito handles user sign-ins and all those things, and Amazon Route 53 manages our DNS. So it's become so easy now. They will sync very well because they are all from AWS product. And if for notification, we'll use handled by Amazon SNS. So we can send SMS, or there is a push service, and Amazon SES for emails. For databases, Amazon DynamoDB for NoSQL. Earlier we use like MongoDB. Now we can use DynamoDB, and Amazon RDS for any SQL. Like earlier we were thinking of planning MySQL or Postgres. Now we'll use Amazon RDS, and Amazon Elastic Cache for in-memory caching, just like Redis we were using earlier. So search, for search thing, we will use generally Amazon Open Search service in for search, like earlier using Elasticsearch, and AWS Lambda reads DynamoDB streams to update the search index automatically by default. So you don't have to do much of those things there. They will sync very properly. For storage and streaming, Amazon S3 is the central hub for all the data like static assets and like data lake and all those things. So it will like object kind of data. And Amazon Kinesis, that is data streams and Firehouse, it will capture and moves real-time click streams data into S3 buckets, or OpenSearch will send over there. For ETL and AI, we will go through like AWS Glue, and or you can use also Amazon EMR perform ETL tasks on all those things. Amazon SageMaker is used to build and train and host the machine learning models. So our work will become very easy over there. And for analytics, we will use Amazon Redshift serves as the data warehouse. Data scientist will work over there and pull those data, and then Amazon Quick Site provides the visualization like Power BI tool, all those things we were doing earlier. And Amazon Athena allows for serverless ad hoc queries on S3. So integration, generally we'll use Amazon Event Bridge, act as the event bus to connect internal and external services. So these are all those things we can implement, and it will become very simple because we don't have to do any external things. They will sync very well because they all are AWS product. So this completes our AWS e-commerce architecture. Remember, this is just one way to build it. There you can find some another way as well because AWS offers many choices, right? For example, you could use EKS instead of ECS or run services on Lambda, whatever your business requirement, and your choice depends on your specific requirements. Now, as we look at the final architecture, I want to mention a few critical layers that I intentionally left out earlier to avoid making the diagram look very scarier. In real life production environment, you would never skip this component, even though they add another layer of complexity. First, we have the Amazon VPC and subnets to keep our application secure. We place our EC2 instance and EC2 microservices in private subnets, so they aren't directly exposed to the internet. We use public subnets only for our application load balancer and net gateway, which allows our private order service to safely communicate with those external shipping partners we discussed. Protection and privacy, we add AWS WAF, that is web application firewall, in front of Amazon CloudFront to block common web attacks. We also implement strict data encryption, that is data at rest, for all our stored information in S3 and RDS, and in transit also using SSL and TLS certification and all those things as data moves through our API gateway. We implement Amazon CloudWatch. This act as our eye in the sky, monitoring the health of our ECS task and Kinesis streams, and alerting us instantly if the system encounters any error. While those layers make the diagram much more crowded, they are what transform a simple app into a secure enterprise grade platform. See, a great architecture always considers the budget, edge cases, and data velocity, the streaming versus batching debate, external third-party integration issues and all. But due to the paucity of time, I left those. For example, Amazon Athena as a much cheaper option for performing ad hoc queries compared to Amazon Redshift. Redshift is great for heavy, consistent data warehousing, whereas Athena allows you to query data directly in Amazon S3 using SQL without needing a permanent, expensive database cluster. Also, step functions manage logic for when things go wrong, such as inventory issues. Say, what happens if an item is out of the stock after the user clicks buy? Or for shipping delays, suppose, how does the system react if a third party shipping partner reports a delay? Or say someone does cancellation, like triggering specific workflows if a customer cancels an order mid process. See, like this you can always deep dive into the details. I am leaving those. Anyway, thank you for watching ABC Tech Lab. See you on the next one. Until then, bye bye.